I will start with the presentation. I am Pēteris Pakalns from Latvian Informatics Olympiad, LMT, and today I will tell you about development of an unmanned aerial vehicle computer vision solution for parabolic antenna inspection. First I will introduce you with myself. I finished my bachelor studies 2 years ago. As we are in machine learning focused at the DevClub, my experience with machine learning is university and courseware courses, image-to-image translation, reinforcement learning, and this presentation will touch on the subjects like computer vision, where I have learned linear algebra, additionally in university, linear algebra and image processing stuff. But machine learning was not my priority in university. I mainly focused on competitive programming. There I spent most of my attention. In professional experience, I'm an on-hands engineer. I have worked in encryption, software protection, with system programming stuff, low-level programming like assembly, C++, with compilers, a lot of stuff dealing with Linux operating system. Then I switched to startup. In KPI Berry, I developed and designed a backend system of the solution. And 1 year ago, I joined Latvian Informatics Olympiad, LMT, where I'm working with computer vision video data processing services. And in this company, a couple months ago, I got the opportunity to work on drone computer vision project that I will share with you today. So let's go over content of the presentation. We will go over problem definition. I will focus on the problems that we are solving with machine learning, one part of the whole solution. We will go over solution idea, and then we will go into technical details about applied algorithms, traditional computer vision algorithms, and machine learning algorithms. I will go a little bit in technical details. Maybe some of them will help new developers to start their own computer vision journey. And I will mention problems that you can expect with machine learning, with computer vision in physical world, and if you are working with drone software, what kind of problems you will probably find in open source software. And of course, our presentation will have video demonstrations in middle and end of it. So let's start this problem definition. We will try to solve, this is research project, and we are trying to solve parabolic antenna recognition. We want to determine its position, its pose, where it is like pointing to, and the dish size of this antenna. The inspection is done using the drone. So we need for the pilot to see information in real time, so that pilot can do decisions based on this information. This data that we are trying to solve is used in different parts of the solution to give instructions to pilot where he has to pilot his drone, or to automatically navigate the drone to interesting positions to do few different measurements. You can read more about this project in the URL at the bottom of the presentation slide. So the solution idea. First, to start working with antenna, we have to okay, on the drone, we will have some kind of sensor to detect antennas. Probably it is a video camera. And if we have video camera, how we can detect this object in video stream? First, we have to detect this object location to do further processing of this object. So we'll need some kind of object detection. But to estimate the position, it cannot be done just from one observation. You need some kind of object tracking or position fitting, and to apply some kind of position fitting to all observations that you have done of this object. Then if you have enough data, you can do this pose estimation. But to do pose estimation, we need to do some kind of assumptions of the objects that we are seeing. In this case, we can do assumptions that the antenna dish is circular. It's like we can assume that it's a perfect circle. So we can try to calculate the properties of the circle. To do that, we first need to estimate the ellipse in the visible image of this antenna. And later we can try to calculate the pose of this antenna. Like we can calculate this 3D circle and estimate the position, size, and pose. Of course, as I said previously, multiple observations are necessary to do that. One interesting fact, what I like to do when thinking about problem is like to make some kind of visualizations to better visualize how this problem could be solved or what are the best approach to solve it. One thing, as in every engineering discipline, we can do some kind of assumptions and assume that, okay, to simplify the problem, let's assume that we are looking at the objects for very far enough distance that we can use orthographic projection. Then this problem gets very simple and we can create simple visualization. I will switch to that in the moment. And we can see some interesting behavior in this visualization. For example, if you are looking at the antenna from the front, with like large angle change, like 10 degrees or larger, it's very hard to see how the ellipse is changing. And it's probably will be hard for your computer vision solution to detect the angle at which it is pointing to. Like you can see the angle change of difference for 1 degree of change is only like a couple of pixels for image size with 500 pixels. But if you are looking at the antenna from the side, you can see that it is changing by a large amount with very small angle change. So we can like see that probably the best approach to inspect antennas and to calculate the necessary information will be by inspecting these antennas from the side. It feels counterintuitive that you want to find the direction at which this antenna is pointing to, but the best approach is to like survey it from the side. So let's switch back to the presentation. So yes. So let's go over this pipeline, each steps, dimension, and buffers that we will need in our computer vision pipeline. First, we need to detect objects in your video stream. And video streams consist of separate images. So first, how to detect objects in image. We could use detection that outputs bounding boxes that are drew around interesting objects. And we need to do it in real time. And in real-time solutions, a lot of popular solution is YOLO family of object detection algorithms. It is YOLO as in you only look once, not you only live once. So keep that in mind. So we could use YOLO-based approach, YOLO model. You can find multiple implementations of it in GitHub if you want to try it. What you will need is for training that is a lot of image and a bounding box with classification of what kind of objects these are that you have been like marked in your image. And if you are using YOLO family object detection, how it works, you have input image of this from the survey, and it does convolutional neural network to extract the feature information from this image, feature upscaling to different scales of the image, and this network does prediction of bounding box for 3 different scale of objects. For small objects in the image, for medium scale objects in the image and for large scale objects in the image. And in the end, you will get a lot of objects detected that could overlap or could detect the same object. And you need to do some output parsing that you can do with the same code in that library that you are probably using, or implement your own if you are only using the neural network part of that model. Next, if you have these detections, if you have detected detections, we have video stream of input images, and we need to track this object over time to get multiple observations that we need to estimate position or estimate the ellipse and finally circle. To do that, the simplest approach that I found out is just simple object real-time tracking, where you have where you can describe bounding box with 4 parameters. It's position of the center of this bounding box and its size, horizontal and vertical size. Then you can define some kind of transformation to predict the bounding box in next image, like some kind of model that describes how the properties of B boxes, bounding boxes, change over time. Using, for example, you can use Kalman filter, and using that you can get predictions for next image where the bounding box of these objects will be located in it, and you can get detections from this image that will probably not match very well to the predicted bounding boxes. And what you do lastly is you do maximal matching problem, where you try to match your predictions with detections to get best matching and to determine which predictions were for which objects and which objects are which. For like weighting which object matches with which object the best, you can use intersection over union that calculates how well these two bounding boxes overlap. As we can now track these objects in video stream, we can do position estimation. And to do that, we first need to decide in what kind of coordinate system we will work in, so that we can describe the position of this object. And this coordinate system is dependent on the drone, because we will describe the position of object in relation to drone measurements. So to get some kind of position, we will need to calculate it from the drone position. So on the drone, the position you get from GPS sensor and from barometer. And we probably do not want to work in GPS positioning systems coordinate frame, where you have to work on ellipsoid. We would like to work on more simpler coordinate frames that we have learned in school. And for that, we can do coordinate transformation, where we pick up, for example, where the drone started its flight position. And from that, we can define a very nice autonomic coordinate system. In which it's very easy to work in. Next, to describe position from the viewpoint of the drone, we need to take into account the pose of the drone itself. And that can be retrieved from AMU sensor, inertial measurement unit sensor, and magnetometer. And you will get some kind of position in this coordinate space of the drone, pose of this object. But that's not all. As we are viewing the final interesting object in camera, we still need to look further and describe the object from camera coordinate frame. And there's one more transformation necessary, when we are like calculating everything in camera coordinate frame, we still need to remember that camera is a perspective projection. So the coordinate frame is not like simple northeast down coordinate system, but it is a projection on 2D plane. And when we are trying to estimate the object positions that we have previously detected, instead of detecting precise position of the object, we will detect a ray that goes through the interesting object. So as you can see, we do not know how far the object is from the camera. What we know is in which direction the object is placed in. And if we have multiple such observations, we can do position estimation. The simplest approach to do position estimation is just try to estimate the position with least error to all observations. Observation error can be calculated with simple distance to the observation, and you can probably use an approach, a least scarce approximation, that each of you probably has used in Excel to fit some kind of function to your data. Using this, we can already get object position approximation. Next, and here you see picture from simulator. I will talk about it later. With all of the estimated positions, the pink points in the image. As I previously slide, these are initial approximations of the object position to later simplify some calculations. Okay. And now we get to the post detection of the antenna. First, a lot of times you should try out traditional image processing algorithms, but sadly this time they didn't work out very well because antennas in a lot of cases could be occluded by each other, overlapping, or there could be bad background or bad lighting conditions. So at least with my experiments, I didn't succeed using traditional image processing algorithms. Instead, what you can use is use machine learning again. You can define ellipse estimation problem in two different ways. In one way, you want to estimate binary mask of the antenna dish, and then use classical algorithm to estimate ellipse contour. In this case, to generate binary mask, you can use, for example, encoder decoder neural network with skip connections. Another approach is to directly calculate ellipse parameters from the input image. But with this approach, I found out that sometimes if there are small numerical errors, the change of the ellipse position in the image or its rotation changed by a large amount, and the binary mask approach worked better. Probably we are still experimenting with this, and we will do some kind of approach where we are using the both methods together. For these machine learning networks, you can find already available machine learning models in GitHub or in Google by searching, for example, segmentation network or just convolutional neural network, where you can use all the trained convolutional neural networks and just use transfer learning to estimate ellipse from all the calculated features in pre-trained neural network. Okay, and at last we are reaching the circle estimation to describes the antenna dish position in 3D coordinate space. First, if we are looking at one observation of the antenna, we have to remember that the circle is projected on the image plane as an ellipse. And what happens when you can try to reconstruct the pose of the circle, you can calculate two possible directions that this circle is pointing to. So as we can see from one observation, if you are only estimating the ellipse, we cannot determine in which direction the antenna is pointing to. For that, we'll need some kind of algorithm to estimate this position from multiple observations. For that, there are all the existing algorithms. But in our case, we developed our own method. In this algorithm, this picture is very good visualization. We have multiple observations of the object. In each, we have the ellipse of this object, and we try to find the original circle of this antenna dish. In this solution, we found out that if you have noisy measurements, the solution doesn't converge very well, and therefore we used our own approach. But this approach still is usable, and if you want to try out something like this, you can experiment with that. For testing drone solutions, you probably do not want to fly your drone every time when you have some kind of change in your program. So good way to test your solutions is to use some kind of simulated environment. Popular simulator that was developed by Microsoft is RSim Simulator. It's open source. You can try it out. And in this environment, we can just set up the environment, telecommunication towers with antennas. And we can fly in this environment to test our solution. Additionally, you can use artificial environment to get initial training data for your machine learning models. For example, in RSim environment, you can get segmentation image of your environment. You can get object information about objects that are located in the simulated environment. And you can use this information to get good bounding boxes for these objects that you can use later to get initial training data to move faster forward with your solution. Of course, if you will test your solution in a real environment, manual data annotation will still be needed. Why? Because in real environment, you still have different properties of this environment, and your model machine learning algorithms need to learn these properties. Of course, if you're developing your own machine learning algorithms, apply data augmentation. It will help your model to generalize a lot better. And using all these methods together, we can already test our solution in simulated environment. So let's check out first demonstration in this presentation. Okay, one moment, I will switch to video. So yes. What you will see will be the drone flying vertically besides the tower and doing video processing. Why we are doing vertical movements is because during vertical movements, the drone is a lot more stable and it is a lot easier to do more precise measurements. So let's see how our solution would work in this case. What you see in this screen, you see green circles and lines. These are ground truth antennas that are placed in environment. The green circle describes the antenna dish, and the line describes the position in which the antenna is pointing to. And here you can see the camera view of the drone, and here we can see detected objects and detected ellipses of these objects. Okay. So we'll do vertical flyby of this tower, and as you can see, this red rays describes the ellipse that is seen in 3D environment, and the circle will fit to this. It's ellipsoid form conus that has it as its base ellipse. As you can see in simulated environment, such solution works very well, and it easily recognizes the ellipse, the 3D circle, and the direction in which it's pointing to. Little bit closer view of the detection process. Okay, so in simulated environment, everything works very nicely. So it's end of presentation, and we can go like do celebration about project that is done. But sadly not. This is simulated environment, and in physical world, we have a lot of problems that we still need to handle. Our measurements, estimated constants, have some error, and we will need to estimate best state guess using noisy measurements. Why noisy measurements? Because imperfection of physical device and the placement of objects on this physical device. So let's go into technical details about these physical imperfections. First, it's very important part of the solution, the camera. And you have to carefully choose what kind of camera you use. For example, if you are choosing camera, the shutter is very important. If you will use rolling shutter with low frame rate, you will get distorted image when the camera is moving around. Additionally, the camera lenses introduce some kind of distortion that you need to fix that you need to handle to correctly calculate necessary data for your solution. And additionally, to calculate necessary data, we need to know camera intrinsic parameters. We need to know its field of view in each vertical, horizontal direction. To do that, we can do camera calibration. Here you can see camera calibration from one of the initial tests. And in this image, you can see that in original image, the lines are curvy. They are not straight. And camera calibration handles distortions in images and makes lines straight as they should be in reality. And additionally, it provides correctly projected image on 2D plane, so you can do correct calculations of object position. Additionally, it's not the end of problems with camera. During flight, the camera could be overexposed. What does that mean by that? Is that the antenna will be too bright and you cannot see the contours of the antenna. Additional stuff that you have to expect with machine learning in general, there could be new environment, new conditions that your model has not been trained for. For example, in one day we had very beautiful cumulus clouds, and in front of these cumulus clouds, our solution didn't work very well because we didn't have such examples in our training data. So we need to additionally teach our model to handle new images. And we will probably need to do it in future too. As you can see, winter's coming, snow is falling from air, and we will get a new environment where everything in the background will be white, and we will need to additionally train on that. So it's that gathering and that training process still happening. And additionally, in physical world, the device on the drone are not perfectly placed in the same direction. If you are talking about drones in general, if you have used the drones, you know that you have to do compass calibration, for example. Why you need to do that? It is to estimate the errors between different sensors on the drone, between compass and IMU, to correctly estimate the direction in which the drone is pointing to. Additionally, if you mount the camera on your drone, you will probably not mount it perfectly because due to physical problems, IMU can be like placed inside the component little bit incorrectly. Your camera can be placed incorrectly, and additionally, lens distortion adds additional error to your observations. So what you need to handle is camera view offset, image offset from drone coordinate frame. How you can handle it is doing additional calibrations. Additionally, more physical world problems. If you have non-stationary camera on moving object, you have vibrations, rotational movements. Why rotational movements are bad? If you have translation movements, in these kind of movements, the drone has to gather some kind of movement to move very rapidly. And you can easily predict such kind of movements by using Kalman filter. But if you have rotational movements, then small change introduce a large change in the image, and it's very hard to handle that. First, how to handle vibrations. You can add some kind of dampeners to your camera attachment to dampen the vibrations. But you have to be careful with that because, as we talked previously, your camera could get offsetted from your drone coordinate space, and you will get wrong measurements. The second stuff you can do is use some kind of stabilizer that stabilizes your camera. How to handle rotational movements? First, you could handle it with larger frames per second, so it's more easier to track objects in your image. So these rotations introduce smaller change. The second way to handle is change your tracking algorithm and make this algorithm in a way such that it takes into account rotational movements of your drone. You can gather rotational information from sensors on the drone or from images themselves. Here you can see some example without rotational handling and with rotational handling using tracking algorithm improvements. As you can see, with these improvements, tracking happens a lot better. And as I mentioned before, we have imperfect sensors. Sensors estimate the state of the drone in environment with some kind of error. We have a global positioning system sensor and barometer sensor. This estimates the latitude, longitude, and altitude of the drone. And we have pose determination sensors that uses compass, magnetometer, and inertial measurement unit to calculate roll, pitch, and yaw of the drone in the environment. But with classical global positioning system sensor, the precision is only in multiple meters. And with rotational errors, as I previously mentioned, if you have small rotational error, with distance, this error gets very large. And why it is very important for us, we are trying to measure objects that are located 30 meters away from us, 30, 40 meters away from us. And in real life, if you will like stand in the street and try to measure objects in such a distance, it's very hard to do. So you need your sensors to function very precisely. So how you could improve state of things in this aspect is with position determination sensors, you could use real-time kinematic system that achieves centimeter level precision. But for such kind of solution, you will need additional base station that knows that it is in fixed position and can send correctional information about GPS signal state to the drone so that it can calculate the GPS position by calculating out the errors introduced by weather or atmospheric state. In this pose determination sensor, you can do sensor calibration or buy more costly devices that do this a lot more precisely, and you can do data processing technique use to filter out observations that you know probably are very bad. For example, when drone is doing some kind of sudden movements, or when drone is rotating, or stuff like that, that you know that it will result in bad observations. You know that you can simply use only observations that you know that there are, with a lot higher probability, they are better. And what to expect if you are working on drone software and with open source drone software. They are pretty buggy in a lot of cases, because drones are very new field, and this software is relatively very young. And I will mention two interesting bugs that I found out during my work in this project. First, in this image, you can see my second workplace in Latvian mobile telephones. This is the workplace that I am working in. I don't have ergonomic chair here, so that's bad. But imagine you are in middle of forest and you are testing your solution. You are testing your solution for third time, and it worked very nicely previously, and suddenly it doesn't work today, and you are like, what's happening? So you do some debugging session in middle of forest and find out that real-time kinematics service is not working correctly. And what exactly happened is we were met with day of the week bug, where this bug is triggered in specific days of the week. In Latvia, there are already available base stations for GPS correction retrieval that is provided by Latvian Positioning System service. And this system is sending data using old encoding that is not supported by modern drone software. And we found out during live testing that it suddenly doesn't work in Wednesday, in Latvian trešdien, and it has special characters in this word. So fast debugging session in the middle of the forest, and we fixed that in open source software so that we can test the solution. So the second stuff, as there's a lot of features, this drone software open source projects say that there are a lot of supported features, but a lot of times they doesn't work correctly or doesn't work for your use case. For example, I tested our solution with a joystick in simulated environment, as I didn't have access to the radio control of the drone, and it is supported, but it doesn't work because someone in this software has programmed that hard-coded configuration is loaded, and it overrides my custom configuration for my custom joystick. So it doesn't work. And this drone software for this specific use case is very large. I didn't want to recompile it. I looked at the source code and found out that I can change the binary code of this executable to avoid the code path that overrides my configuration, and then everything worked. But what I wanted to show you with this slide is that if you are developing something with the software, you have to be ready to get your hands dirty with some kind of bugs, and you will have to look at the source code. You will have to investigate why exactly something doesn't work. And now we are getting near the final demonstration of the solution in real environment. Here you can see my colleague Guntis Walters from LMT setting up and piloting this drone. And in the background, my workspace. And we'll look at flight and see how the solution works. So one moment, I will switch to video. So what you will see is, I will speed up a little bit video. You will see that we will do a vertical flyby by the telecommunication tower and measure first two antennas from the side. We cannot do the measurement of third and fourth antenna because we cannot see the antenna dish very well. Then we will move a little bit to the left to better view the third antenna and measure its position in this environment. So let's see how it works. So as I mentioned, first we do vertical movement and try to measure antenna location on its pose. Here you can see the solution is trying to estimate the position of these antennas, but it still has not determined the position of these antennas with sufficiently high probability. So as you will see in the moment, when I will turn off debugging information, these antennas still are not visible in the tool to debug this solution. And in a couple seconds, we will have retrieved enough data to sufficiently predict the antenna position and the antenna pose. And our solution will move to the front of the tower to better see the third antenna. And as you can see, as we could see the antenna previously, we needed less data to calculate the position and direction of the third antenna. And finally, we can look at the detections from a closer view and see that in simulated environment, observation arrays converge very well. But in the physical world, we have a lot of errors that we try to reduce or try to minimize, and we get it to states that we can sufficiently predict the antenna position and antenna pose. The antenna position is determined with a little bit less accuracy, but as this is translational error, it is less important for future steps in our project. And ellipse pose we can predict with a higher probability, higher precision. So let's switch back to presentation. And let's summarize what we have seen in this presentation. So in this presentation, we look at that practical approach, how to do parabolic antenna recognition in the real world, and to recognize its position, pose, and dish size. As you saw, physical world, especially if you have moving camera, or you want to not only say something is visible in the image, but you really want to calculate the position or its pose in the environment, you need to handle a lot of physical world imperfections in your solution. And this part that you saw in this presentation is only part of the whole solutions that we are developing. And we are using this data fuser to give instructions to the pilot or to automatically navigate the drone to interesting positions in the environment to do fuser measurements. You can read about this project more in this URL. There are more different interesting projects that we are working on in LMT that you can read there too. If you want to later communicate with me or ask some questions after a couple of days, you can find me in social networks by writing my name, Pēteris Pakalns, or writing directly to my email address. So that's all that I wanted to tell you today. Thanks for this opportunity that I could speak here, and I am ready to answer your questions.
So can you hear me?
Yes.
Okay, good. That's good. Sometimes I had a glitch and that after taking myself off and coming back, you can see me, but you can't hear me. So yeah. Attendees, if you have questions, please ask them now or be silent till end of your life, something like that. Was the right saying, right? So do you keep working in the nature in this weather as well?
Yes, sadly in this weather we have to work sometimes in nature too. But it's very interesting and it's very a nice change of pace to go outside and work with technologies in nature.
I'm not sure. Do you see that Alberts is writing, wow, this is cool, and Alvis is writing, thank you for presentation, very fascinating. I can show them here. And okay, I misclicked, but Benjamin is writing. What is very cool and challenging project? How big a data set did you have to build for each stage?
Okay, as we are very fastly iterating with the solution, and several approaches didn't work very well or worked very well. So we don't have time to make a big data set of data to teach our models on. We use two approaches to get our data set. First was to artificially generate a lot of examples of antennas in different positions so that we can get train these models, and then we did manual annotation by hand of these antennas and segmentations as many as necessary. So it was maybe a couple of hundred of images, like less than 500. and we annotated the amounts so that we can test the solution in real environment and see if it works. So I was very fascinated that the data amount that you needed wasn't really very much.
I'm just reminding people, please give us feedback about Pēteris' talk in a form. I'm sharing here link on the screen as well. And okay, I will go and pin it. So this is now the most important message. So are there any more questions? So while they're okay, here is Jan is writing. Is this solution reusable? Could you give an example for other usages?
Other usage will be some kind of equipment survey in nature. For example, maybe you could use this on electrical lines where there are a lot of some kind of components on where the like wires are handled on, or object position estimation in general, where you can like follow the object for some time and estimate its position. So, but this is like this knowledge is very rarely usable in like equipment survey in nature.
Yeah, Benjamin wrote indeed very small data sets, cool. And also Benjamin is asking, what are the business consequences of errors, FPS and FNS?
The business consequences, they are we are using this to further. Okay, first this information is done to inspect antennas to see if they are really placed in the positions and they are pointing in the direction that they are documented to be pointing to, so that real world placement of these antennas are really in positions that they are documented to be in. So if we that is one use case, and in this use case very important part of the measurement is the angle at which the antenna is pointing to. If you will like incorrectly calculate the position of the antenna by a meter, it's only translational error, and it will not cause a large problem. But the direction of the antenna is the important part, and there we have a couple of degree margin. One user use case is where it's very important to get precise measurement of the antenna pose to move the drone in front of the camera in front of the antenna to do future measurements. And there we have two couple of degree margin where we have to place this drone inside. So the main like problem is the solution will be the pose estimation of the antenna. And in that case, the problem will be that you cannot, when you will place your drone in the target position, it will not get very good measurements, but there are still ways to fix that with doing some kind of additional movements of the drone, and it will be good that these pose estimations are good, as precise as possible, but still there can be some kind of error that we can fix in later steps. I hope that answered your question.
Does it mean that some drone operator is constantly correcting position of drone, or how do you mean that?
It can be both by drone operator manually, and it can be automated too.
Okay, while there are no more questions, so if any question comes in, please write it now. I have the very important question. So about chocolate preferences, dark or milk?
I will prefer milk chocolate.
Milk. I think it's very good choice. However, my preference is dark chocolate, but I find that Latvijas ķepainītis is somehow it tastes not as usually milk chocolate taste. This one is somehow very good. My son suggested me it a few years ago. He was already expert in chocolates, so very good choice, milk.
I agree.
Okay, Yanis is asking, when you are doing measurements, do you impact the data transfer?
If you are talking about this computer vision part of measurements, then now we do not impact, but in this environment there could be problems with data transfer because we are operating in environment where there are a lot of electromagnetic emitted signals, and we have seen cases when we are like flying with drone, and there are really problems when we move in some kind of positions, and the drone and the data transmission rate gets reduced or impacts the performance of our solution.
Are these measurements made so far only for 3G and 4G antennas or also for 5G?
I think 5G antennas are not even parabolic antennas. They are more like vertical ones. I'm not sure. So I will say that not.
Yeah, I wanted to ask, so how big radiation do receive operator if do measurements for 5G? But this is trolling question, not serious one. Okay, so it seems that there are no more questions. So thank you very much.